Hello, everyone. Welcome back. Last time we talked about Ito's lemma, and we quote-unquote showed how Ito lemma is, why Ito lemma has that particular form there. Now, in this video here, let's look at some examples of Ito's lemma. So if you have a for contract F, in many textbooks, you will see that the value of F is related to the stock price, the spot price S of the stock in this particular form here. So essentially, F is a function of S, which is the spot price of the stock, and follows a Ito's process. So, and we talked about earlier that a sensible way to model S is with a stochastic process, ds equal to mu s dt plus sigma s dz. Here, mu is a parameter, is a constant. Sigma is another constant here. So it's proportional, so it's a constant times the state variable s here as the drift, and sigma times the state variable s as the volatility term here. Now, so if S follows this particular stochastic process, then what is dF, right? So with Ito's lemma, you can derive the process follows by F. So all you need to do is really just to take a few partial derivatives. So if you take dF, the first partial derivative with respect to S, you will have dF ds equal to e to the power of r times bracket t minus big T minus small t. And since this is not a function of S, if you take the second derivative, second partial, then we get a 0. And dF dt will give you this particular form here, minus r times s e to the power of r bracket t minus t. So you now have everything you need to construct the process for the futures contract or the forward contract here. We ignored the difference between forward contract and futures contract in this particular example. We'll actually ignore that for the entire course here. So dF then is dF ds times mu, which mu in this case is this mu s. And so mu is a function. This function itself, you can see, is mu times s, which is this part here. Okay, and from this df dt, we have this term. Okay, and from this partial derivative here is dropped out as 0. So, and this part we have this again sigma s times e to the power r t minus t here. Now, all the blue ones here is really just f. So you collect the terms, you have mu minus r times f dt and times sigma f dz. So you now know what the process that the forward price or the futures price will follow if you have a underlying stock that follows this log-downward process. Let's take a look at at another example here. Under risk neutral, we'll have ds is equal to rs dt plus sigma s dz. Now, in the earlier example here, in this stock price process, we have ds equal to mu s dt plus sigma s dz. The process we specify here is not under risk neutral. It's just under the actual world process. So if you were to observe, you will actually see the stock actually increase with this particular drift in the real world. We're gonna talk about the risk neutral aspect of things later on, but just right now, take it that in the current world, this is what you would expect to see the actual process. And then obviously, there's a risk neutral world where for pricing you will use, and how you connect the risk neutral and the real world. You know, that's the subject of another video later on. Now, in the risk neutral world or risk neutral, the risk neutral process, we change mu to r. Okay. Now, in this case here, you can derive the process for f under risk neutral. So you do exactly the same thing here, except that you have to replace mu with r. So if you have done that, you will have, instead of mu minus r f, you have r minus r f, which means this term will drop out. So here, you will see that in risk neutral, the process there's no drift for the futures price. Okay, it's only a stochastic term here. Now, the reason we're showing this particular example is to demonstrate that ethos lemma is actually applicable to any probability measure you just happen to apply here. And it applies to the real world probability measure. It also applies to risk neutral probability measure, or any other probability measures you happen to transform into. And so ethos lemma is all applicable in all of those situations. So regardless what the measure you're working with, you can apply ethos lemma the same way. Okay, let's take a look at the another example here. So in real world, we have this particular process for stock. So this example will tell you why we call this process the log normal process. So now you have ds equal to mu s dt plus sigma s dz. Mu and s here are not functions now, they are just parameters, okay? They're constants. Now, if we have a function which is log s, okay, and if g is log s, then what does g follow? So you go through the same process here with ethos lemma. You'll calculate the partial derivatives, and d log s is equal to mu minus half sigma square dt plus sigma dz. And if you look at it, so what distribution is s here? So from here, you can do the integration because here is only a parameter times dz. So it's very easy to integrate here. And if you integrate, you will see that the distribution of log as t, t being a future time point. So it's normally distributed with log s naught, which is initial time. So you will have a time here, current time, and a future time t. So it's the log of the stock price at the current time plus mu minus half sigma square times t. So this is the expected value. So, or the mean here. And the variance is sigma square t. So the log of st is normally distributed. That's why this process has the name log normal process. Okay, and let's look at some examples of log normal distribution. So if you have a log normal distribution, we mentioned that the advantage of having stock price being specified that way is that there's no possibility under that formulation that stock price will be negative. So if you look at the distribution here, there's no any mass, there isn't any mass here where the stock price ST is less than 0 if you start with S naught be any number greater than 0. Okay, so here is just some properties for the log normal distribution. So I'm not gonna belabor too much on those points. So you should take a look at this and then figure out, so what is expected log ST divided by S naught? So, or what is the variance of the log of the ratio? Okay, this is something that can easily be figured out. So let's look at an example. So suppose you have an initial stock price of $40. Mu is, so on average, the stock price were to increase by 16% each year, and your annualized volatility is 20%. So the question then is, what percentage of the stock price in 6 months, which is half a year, so big T equal to 0.5 here, will lie between 32.55 and 56.56. Well, in this case here, we assumed the stock price follows a normal process. If that is the case, then from what we have seen earlier, log of ST, T here is 6 months later, which means this big T is 0.5. So log ST follows a normal distribution here, okay? And from this normal distribution here, you can then figure out that, by plugging in the numbers, so log 40 is this log S naught plus this part will give you 3.759. And this sigma squared T will give you the 0.02. And so then if you look at your so you look at the two interval here, 32.55 and 56.56. So what standard deviation this represents, right? So if you put it there, 32.55 is equal to e to the power of this 3.759. So minus x times 0.141. So that so what is your X and Y, your X and Y in this case is 1.96. So you are moving 1.96 standard deviation to the left and 1.96 standard deviation to the right. So the area underneath this curve here is really 95%. So you know that, with this distribution that you will know that 95% of the stocks price, realized the stock price in 6 months will be between 32.55 and 56.56. Okay, so I'm gonna stop right here, and I'll see you in the next video.